There's two basic types of turbines in terms of electricity production, and that's in addition to ones that pump water and do other things. The kind we have is what they call a direct drive unit, so it basically operates like a motor in reverse. So instead of electricity turning the motor, which drives a fan or something, we've got the propellers and the wind blowing across it, turning that and rotating the generator, which produces electricity. And so it's equivalent to a motor running in reverse. And that's good for most of the small units. When they get into the really large units, what they call utility scale units, most of those add a complication with the gearbox for speed control. Those units tend to rotate fairly slow, less than 100 revolutions per minute, sometimes even down 20 or 30 revolutions per minute. So they're slow, and then they take that slow revolution and run that through a mechanical gearbox, which speeds up the drive shaft to run a generator at more conventional speeds like 3,600 RPM or 1,800 RPM. Those gearboxes are large mechanical components, are also costly, and there's some inefficiency associated with them, but it's the way they get the low spinning RPM of the large wind turbines up to a speed that's compatible with generating electricity, whereas in the small ones, the weight's smaller, the mass is smaller actually, and our particular unit can run at up to about 350 RPM, and then through electronics they get that to synchronize with the grid to generate electricity that's compatible with what the utility is providing. The unit is rated at 1.8 kilowatts. The maximum I've seen it put out is about 2.5 kilowatts. And 2.5 kilowatts would run a home, and what I tell folks, everything but the air conditioner, because the air conditioner tends to be about that same size. So if you look at your home, you got your lights and TV, refrigerator, microwave, all that stuff running, that would be about 2.5 kilowatts. So the question is, it only runs at that maximum power, that 2 to 2.5 kilowatts, when the winds are blowing about 20 miles per hour. So on average, the wind blows around here about 10 to 12 miles per hour. Sometimes it's 0 and sometimes it's 20. And we've been averaging from the data that you probably were looking at this page. We've been averaging, let's see, this would have been May and June. So a little bit less than 2 months. It was a little over 200 kilowatt hours. So our estimate was about 125 kilowatt hours per month. I looked at my home energy usage the other day, and we were running about 400 kilowatt hours. And so that would service about a third of what I use at home. Now the things that it wouldn't serve at home would be the air conditioner, and also if you had an electric hot water heater, because those tend to be large loads, it wouldn't satisfy those either. So, would this power your home completely? No, but if I had one of these at my house, it would service about a third of the load this time of year in June, July, when we are running the air conditioner. And it'd probably do a little bit better in the winter. We use a little bit less electricity in the winter because we don't run the air conditioner, and the winds tend to be a little bit better in the winter. Yeah, so this is a small wind turbine on a large campus. I estimated, just the back of the envelope calculation, it would provide about 0.1% of our electricity needs for this building. So to get up to 1%, we need something about 10 times this size, or 20 kilowatt. To get up to 10%, we need something 100 times this size, or about a 200 kilowatt. And so that's our goal. We're looking at trying to accumulate enough resources, money, funding, to put up something in the range of a 200 to 250 kilowatt unit here, and with the goal of providing about 10% of our electricity.